Okay, thank you, Mitch, for that introduction. Yes, today I'm going to be talking about solving one of Einstein's mysteries. And just to kind of set expectations, I'm going to turn on the clicker first. And then I'm going to set expectations and tell you that this talk, I'm sorry, is not about quantum physics, gravity, or the fabric of the space-time continuum, despite the title. So usually these are things that people think about when we talk about Einstein and the things that he was thinking about and couldn't solve. But I am going to talk about a bigger mystery that bothered him, and one which all of these smaller ones, which are quite not small, actually all pointed to. And the way that I'm going to talk about this is by not talking about it yet. So actually, I want to just contemplate for a little bit about the theme of this conference, which, as we know, is grace, or seeing God's goodness throughout different disciplines that we're familiar with. As Mitch mentioned, my area, the place that I dwell, is mathematics, sometimes physics a little bit, sometimes artificial intelligence, but primarily in mathematics. And despite what you might think, you might say, math is kind of boring and bad. How can you see God's goodness in that? And actually, it's everywhere across the mathematical discipline. So much so that I had a really hard time thinking of what to say today because there's so many things I could say. How can I just narrow it down to one thing? So what I decided to do is just take a look at what's on my to-do list coming up and just talk a little bit about where I see God's goodness in that. So that's what I want to do now, and then I'm going to come back to this mystery. Okay, so in God's providence, in a couple of weeks here, I'm going to be substitute teaching in a college algebra class here. And so I was looking at the lesson for this class that I have to teach, and I got out my old college algebra textbook from a long time ago, which I have not looked at or thought about in years, and I flipped open to the chapter that we're going to be discussing, and it's on logarithms. Okay, and I just got to confess to you, I kind of groaned a little bit when I opened the book. I was like, oh yeah, I remember learning this when I was in college, or maybe I first came across this in high school. And I'm just going to tell you, the lesson is not that exciting. There's like a bunch of letters and numbers and all of these rules and formulas, and you just have to regurgitate stuff that your teacher tells you to do and hope that you can get an A. And I kind of felt bad for the students coming up in a couple of weeks, because usually math is taught in a very dry, not exhilarating fashion. But the truth is, the information in this lesson is really interesting if you don't follow the book. So I want to tell you some stuff about these things called logarithms, but I'm not going to follow the book. Now, if you maybe at one point learned this, but it's a little fuzzy, or you've never heard about it before, it's okay, because you all have it on your iPhone calculator. So if you open your iPhone or whatever phone you have, don't do it now, but you open the calculator, you'll see there's a couple of buttons, and I know it's a little bit small, but on the right it says log base 10, and to the left of that there's another button that says LN. That stands for natural log. These are logs. So this is the point I'm trying to make. Logarithm is a button you can push on your calculator. But what does it mean, though? So now I want to tell you what this button does. And to do that, I just want you to think a little bit about multiplication. So I'm just going to ask you a few questions, and this is going to be very basic, and just kind of answer silently in your head, okay? So I know it's a little bit small. The question is, how many tens are multiplied together to get 10? So in other words, look at the bottom. If I write 10 times 10 times 10 times 10, blah, 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 how many times do I need to write out a 10 to get 110? One. Just once. Just 110. Just one. Okay. You're going to see where I'm going with this in a second. The point I want to make now, another way to say 1 in this context is log base 10 of 10. Log base 10 in yellow, that's the button on the calculator. Let me ask you another question. How many tens are multiplied together to get 100? 10 times 10 equals 100. So how many tens do I have? 2. 2. Okay. Another way to say 2 in this context is log base 10 of 100. So 2, an answer to that question, another way to say that, log base 10 of 100. Okay, let's keep the pattern going. How many 10s do I multiply together to get 1,000? 10 times 10 is 100 times 10 is 1,000, so that's 3 of them. Okay, 3. Another way to say 3 in this context is log base 10 of 1,000. Do you see the pattern? Okay, so we're going to do it again. How many 10s are multiplied together to get 10,000? 4, and another way to say 4 in this case. Okay, so you see the pattern now, right? So let's just do a really, let's just skip a few numbers. How many 10s are multiplied together to get 1 billion? Notice 1, 2, 3, 4, those are all just counting the number of zeros in the pink number. So how many zeros are in a billion? 1, 0, 0, 0, 9. There's 9, okay. So how many 10s do I multiply together to get a billion? 9. Another way to say 9 is log base 10 of a billion. Do you see what log is doing? It's just counting how many zeros are after the 1. Okay, but I can ask this question for not so nice numbers. How many 10s are multiplied together to get 971,133? You're like, I don't know, there's no zeros, I don't know what to count. Forget that. You just plug in the pink number again. It's log base 10 of the pink number, just like on the previous slides. In this case, the answer is 5.987. You say, wow, how did she know that? She's so brilliant. No, I just used my phone. Okay, so I just plugged out my phone, I punched in the pink number, and I hit the log button, and that's what it spits out. Okay, so that's what this log thing does. It's basically asking you, how many times do I multiply this number by itself to get this other number? The answer is this log thing. Okay, and the point is, really, there's nothing special about the number 10. I could have done this exercise with any number, 2, 3, 17, whatever you want. Each of those, the answer has a log of the base, whatever that number is. So you can have log 2, log 3, whatever. It just turns out that 10 is very common in nature, like we have 10 fingers, for example. 10 is a nice number, so that's why it's on the calculator. There's another number. I've written log base E. E is a number, it's a letter, but it stands for a number. It's in between 2 and 3. It's one of nature's fundamental constants. It applies all over in the natural world. So that's also a very popular use of this. That's why you can see it on the calculator also, next to the blue circle. Sometimes instead of writing log base E, we write ln for natural log. Okay, so just so you know what these buttons are on your phone. So the point is, whatever this log thing is that we're learning in class in a couple weeks, it takes big numbers and it sends them to small numbers. And why do people want to do that? Because big numbers are complicated. And if you want to multiply big numbers together or do things, that can be a little bit tricky. But if you can send them to small numbers and you know how to deal with small numbers, it's more manageable. So we like logarithms. And the lesson that I showed you right in the textbook, the whole point of that lesson is telling students how to go from big to small and the rules that you can use with that process. So that's what the lesson is about. Well, let me just say, there's some interesting things you can do with the small numbers too. So I want to think about small numbers for a little bit. And I want to think about logs of small numbers. What are examples of small numbers? Well, probabilities are small. If I have a coin and I toss it, what's the probability it lands on heads or tails? It's 50-50, right? What's 50-50? 50-50 is like 50% or 1/2. 1/2 is a fraction. Fractions are small. That's what I mean. Probabilities are small. Okay, well, actually, let's think about this. I just asked this. What is the probability of getting heads after tossing a fair coin? Okay, it's got heads and tails. I don't know which one it's going to land on. It's 50% heads. So 0.5. There's my small number. Now, I want to take log of that. In other words, I want to get out my phone and just press the log button. Actually, for some cosmetic reasons, I want to take log of 1 over that, but don't ask me why. It's very minor, not a big deal. So if I do this and I pull out my phone, I'm going to get a number. The number I get is 0.693. Don't worry so much about that number. I just want you to observe that is a positive number. It's not negative. It's positive. Just remember that. I'm going to ask you another question. Suppose I have a coin, but it has heads on both sides. What's the probability that when I flip it, it lands on heads? 1. Okay. I want to take log of 1 over 1, which is just 1, again. If I take out my calculator and do this, the answer is 0. So let me ask you a question. If I have a coin with heads on both sides, and I flip it and it lands on heads, how surprised were you that it landed on heads? Like a lot or not a lot? Like not at all, right? You had 0 surprise. What is log of 1? 0. In the first scenario, when I had a normal coin and I flipped it, I didn't know if it was going to land on heads or tails. So when I saw it land on heads, I was like, whoa. So how much surprise did you have? Like a little bit, a positive amount. Do you see where I'm going with this? So in general, mathematicians think of log of 1 over probability as measuring the amount of surprise in an event with that probability. Log of 1 over probability is sometimes called the surprisal. Okay, so here's the upshot that we've just observed. If you have a lower probability, when it happens, you're more surprised. Like the probability that it's gonna blizzard tomorrow in LA is very small, so if it happens, we're like, whoa, that's a lot. If you have a higher probability event, you're less surprised. Okay, so what about that? Well, we've been talking about coin tosses, but where else do we see probabilities? Maybe you actually deal with this every day now, but if you've ever used ChatGPT or Gemini or Grok or Claude or whatever your favorite large language model is, these things use probabilities too. In other words, whenever you open ChatGPT and you type in some question or some prompt, here I'm saying, what is the main ingredient in guacamole? You type this into the interface, and what this language model does, it has collected all of the statistics in a particular language, like all of this stuff on the internet, on Reddit, on Wikipedia, or whatever. And it says, okay, based on the words that were input, it looks at all of the possible words that one could say, and it labels each of them with a probability. So here I have, like, maybe aardvark has a very low probability, 0.005. Avocado has a higher probability. Why? Because anytime you look at a recipe and it mentions the word guacamole, avocado is in there somewhere, but aardvark is not. So the statistics are in the favor of avocado. So similarly, it's labeling all of these words with probabilities, or sometimes really they're tokens or word pieces. Okay, so you have a list of all the things that could come next, and then it looks at those with highest probability, and then it picks one of those, and that's what is output to you on ChatGPT. It's all based on probabilities, based on the statistics of a language. Okay, I just want to think now about probabilities and logarithms in this setting. So let's just think about 2 words briefly, okay? So on my list of possible outputs that ChatGPT could have, there's avocado. I'm just making up these numbers, by the way. It's some large probability, let's say 0.987. You know, in theory, ChatGPT could also answer supernovas, but maybe that's a much lower probability. Okay, so maybe it's going to output avocado, but you know, sometimes it hallucinates and it just gives you weird stuff. All right, so I want to do the same thing that we just did earlier. I want to compute log of 1 over each of those numbers. But I just want to do a little conceptual shift. When I compute log of 1 over the probability for avocado, that's in green, I punch it into my calculator, I get a tiny number, 0.01. When I do the same thing for supernova, that's the pink number, I get a much bigger number, 6.2. I want you to think of this as like a distance. That's why I have a little ruler up there. I want to think of those numbers as how far away that answer is from my original question. And you say, wait, how far away? Like, what is your ruler in units of? Are we talking about inches? Centimeters? What are you talking about? I don't know, but just conceptually think these are some units of how likely it is that this word is a continuation of this question or is an answer to this question. Actually, let me just tell you, if instead of natural log I have ln, which remember, the question instead of like how many times do I multiply 10 by itself instead of 10, it's this fancy number e, right? If instead of e, we use 2, log base 2 of a probability, the unit for that are called bits. Bits, like bytes, like megabytes, like gigabytes, like terabytes, like computer storage, okay? So in information theory, the units are really things that are tangible that we care about. I'm just shifting it a little bit, so I'm just thinking the units are like how far away this word is to this question about guacamole based on likelihood. But the point I want to make is, if I ask a question or have a sentence, and the next word has a high probability of coming after it, it's nearby. And if it's not likely to come after it, like supernovas being part of guacamole, that word is way, way, way far away. So now I can start to think of language geometrically. And I can kind of think of completing my little graph here, where things with low probability have a larger distance of being near by it, and words with higher probabilities are much smaller away. Okay, so now I can start to imagine that every sentence that I form in my mind or that I'm writing down on a piece of paper is like a path, where every junction in my sentence, I have to think what word comes next. Really, this is what ChatGPT is doing. And ChatGPT may have something like 100,000 different possibilities, each with a different probability, and it picks one, so it steps in that direction. And now it has 100,000 more possibilities, so it picks one and it steps in that direction. Do you see? Every time we make a path, we're taking a different step, until we've completed a book or a thought or a paragraph, and now you have a whole path traversing this space of language. Moreover, I can kind of think as the distances of those steps is how likely is that next word going to be. So what you can now start to do is wonder, hey, how big is this space of exploration? So in other words, if I'm forming a sentence and let's say I'm stuck at the word is, there's many things that could come after the word is, and maybe some of them have a high probability, so they're nearby. Maybe some of them have a small probability, so they're farther away. But I can kind of measure, like, on average, which direction could I go? You know, how uncertain is my model to take this next step? I like this visual because Matt kind of mentioned a similar analogy, I guess, in his talk about hiking. So it's almost like hiking. You can kind of think of text generation as like hiking different branching trails, where each junction in the trail is a word choice. And you're kind of like, hey, how clear are the trails signed at this point? Like, it's telling me you have 3 places to go. Does one person always travel along this path? You know, does my language model always output this thing? Or is it a little bit uncertain and some things have other probabilities? So you have all of these trails that have been traversed or not. So more uncertainty at each trailhead kind of makes your space feel larger. Like, wow, there's lots of places I could explore. Maybe. Depends on your language model. So you could just ask, like, how big is it? How big is this space of exploration? Do I have lots of paths? Do I just have one? What is this number that you get? So there is a number, and actually it has a name. Mathematicians call this magnitude. I'm not going to tell you how you can compute this thing. I put the formula up there, but I'm not going to explain what it means. But it's essentially using this idea of uncertainty or the likelihood of other things to figure out how big your linguistic space is. And so you get a number, and it's kind of measuring your language model's overall uncertainty. Now you may say at this point, magnitude, I've never heard that before. Did we learn that at some point in school? It's just been so long, or did I fall asleep that day? No, because we just came up with this year. So I've just told you now some research I've been working on with another mathematician, Juan Pablo Vigno. So Juan Pablo was at Caltech at the time, and now he's at Northwestern University. And so we've been working on this since earlier this year, but some of the ideas relate to some research I've been doing since I was in graduate school. So I just told you about a research project that I find interesting, thinking about language in the context of some ideas in mathematics. And I want to say, everything I just kind of told you is like some hot off the press stuff. We just submitted a paper, it got accepted for publication, pending some small edits. But this concept of magnitude actually originated in the 1990s by a pair of environmental scientists who were studying biodiversity, and they wanted a good measure of diversity of different species, and they came up with this thing which they did not call magnitude at the time. Now, independently of these environmental scientists, in the early 2000s, there was another mathematician who was interested in some more pure mathematical questions that have nothing to do with AI and that have nothing to do with biodiversity. Actually, he studies something called category theory. Category theory is a branch of pure mathematics. It's really the language of the modern mathematician nowadays, which came on the scene in the 1940s. And so this mathematician in the early 2000s was using ideas in category theory, only later discovered that he stumbled upon the same idea that the environmental scientists were using. And so we took those ideas from category theory and applied them to the context of language. And that's what I just shared with you. But don't forget, all of this started with a discussion on logarithms, which, by the way, were introduced in the 1600s by a Scottish mathematician named John Napier, who also wrote a book on the book of Revelation in his free time. But I'm not endorsing that book because I haven't read it, so I don't know how good his theology was, but I just thought that was a really interesting thing. Okay, so I just told you one tiny application of this concept called logarithms that at one point you may have learned in a college algebra class. But even if you're not interested in this, and even if you've never heard of logarithms before, certainly you're familiar with their use in everyday life. For example, if you've ever said, "Oh, how loud was that noise?" and the answer is in decibels, decibels are measured in log of a certain sound divided by some other kind of baseline sound. So log of a ratio, just like we looked at logs of 1 over probabilities, logs of ratios are very interesting throughout engineering, science, math, and technology. Decibels, acoustics is one example. If you've ever wondered, like, oh, how acidic is this drink I'm about to have? Or my soil for my plants? And the answer is some pH level. Okay, pH is literally, you count the concentration of hydrogen ions, and then you take 1 over that, and then you take log of that. Remember, log takes big numbers to small numbers. So the number of atoms in a liquid is like a lot. And log of that big number is something like 7 or 8 or 6. So pH it involves logs. Also, you know, when there's an earthquake and we're like, wow, how big was that on the Richter scale? So those numbers on the Richter scale are logs also. You take the amplitude of the seismic waves and you divide it by some sort of baseline amplitude log of that, and you get a small number. That's on the Richter scale. So I just want us to appreciate that logs, while they may look boring on a textbook, actually appear all across the scientific landscape. Well, so that brings me now to what I wanted to say at the beginning about Einstein. So Einstein was a physicist who encountered mathematical ideas all the time when thinking about the world around us. And I think that this quote, so he wrote an article in 1936 called Physics and Reality when he's thinking about some philosophical questions. And in this paper, he says, The eternal mystery of the world is its comprehensibility. The fact that it is comprehensible is a miracle. So to Einstein, it was mysterious that the human mind, which to him is just a product of evolution, can uncover deep truths about the world around us, about the world that we live in. So in fact, there was a New York Times article that came out the same month that he wrote his paper, and the author is writing about this. And in that article, they go on to further quote Einstein as saying that the totality of our sense experiences, like the fact that we can observe and make sense of things in the world around us, is such that by means of thinking, it can be put in order. That is a fact which leaves us in awe, but which we will never understand. So sometimes we take our ability to think, our ability to discover mathematical ideas, even our ability to see their connections in the world around us, we can take those things for granted, even like Matt was saying. But as you can see, Einstein did not. In fact, he was in awe over this. But sadly, for him, that's where it ended. It was a dead end. Something, in his view, we cannot understand. And so this is Einstein's eternal mystery. But I think it's wonderful that God dispels that mystery in the first book of the Bible, chronologically speaking. So in Job chapter 38, in verse 1, Yahweh answered Job out of the whirlwind and said a lot of things to Job, including in verse 36, who has given wisdom in the innermost being, and who has given understanding to the mind? The answer implied is God did. So understanding is a gift given to us by God intentionally. And I think this is really interesting. In the next chapter over, chapter 39, it talks about ostriches. And in verse 17, it says, God has made her, meaning the ostrich, forget wisdom, and has not given her a share of understanding. So God intentionally has given man made in his image understanding and withheld it from other creatures like ostriches. I don't know if you've ever woken up and thank God you're not an ostrich, but thank you, Lord, for not making us ostriches. So he gave us wisdom and understanding. Why? It is so that we would stand in awe, like Einstein said, but not a confused and hopeless awe. Rather, an informed awe that's full of worship to the Lord Jesus Christ, who would condescend to our level to make himself known to us. And we see that, traces of it, we see it throughout creation and general revelation, but more fully in Scripture, in special revelation. So the ability to think, to observe, to discover, that is a gift from God, even to those who don't acknowledge him or who worship him. And that is grace. That is grace. So I want to start to close by saying a few words on this sermon that I really enjoy by Pastor John on Luke 9. So Luke 9, verses 12 to 17 is when Jesus is fed the 5,000 with a couple of loaves of bread and fish. And Pastor John in this sermon, you can find it on the Grace Today website. So this is from almost 23 years ago to the day. So he's talking about, you can see Christ's compassion in feeding these hungry people. Like, why should Jesus care if you miss a meal or not? So you see his grace, his common grace there. And I really like what Pastor John says about food in the context of grace. So I'm just going to read what he said and then kind of tie this back to mathematics. So I think this is such a great point. So he says, when God created the earth, he designed a common grace into this world just in the realm of eating. He not only made eating a necessity, he made eating a pleasure. He made eating an amazing delight. I mean, it could have been that God so designed the human anatomy that we would eat dirt and nothing more, or the close equivalent, bran cereal. So that basically life would be filled with nothing but that, some tasteless, tedious brown stuff. And we could have survived on that. But God didn't do that. God literally loaded this world with the potential, almost limitless potential for food. That is an amazing common grace. So just remember that the next time you drive along and you see restaurant after restaurant after restaurant of a variety of foods being presented to which there seems to be no end. It's astonishing. Okay, I don't know if you've ever thought about math like food, but the mathematical landscape is very much like a huge buffet table. It's very much like row after row after row of restaurant. And I just have to say, the math that we learn in high school, middle school, and college, it's only like the first part of the salad table. And you may skip salad because you don't like vegetables and you just want to get to the good stuff, but there's so much more good stuff. And the point is, maybe something like logarithms or whatever may feel like salad or like bran cereal to some of us at times, but God in his goodness intentionally gave us the language of mathematics, not only to enjoy, it's there for us to enjoy, but more importantly, to point us back to him in worship. So I'm going to be thinking about this in the classroom when we go to talk about logarithms in a few weeks, and I hope that you will too the next time you come across a mathematical idea. Thank you.